Alrighty, so this is the second part of the Assessment 2.2 worksheet. The first part was the, excuse me one quick second. First part was the growth and decay, and then the evaluate the exponential function. With this one, and again, as I'm recording this, you've already taken Assessment 2.2, but it never hurts to kind of go over some of the same problems with some of the same principles, and just make sure that everyone's on the same page. Because moving forward, it's basically just going to be polishing and preparing for Assessment 2.3, which is, again, just getting ready for Unit 3. So, well, yeah. All right, here we go. This is another series of graphing papers. So this whole paper is just graphing. We're just going to get a lot of graphing practice in with this one. So what we do first, we take a look at our equation. We've got f of x equals 0.5 to the x power. So it's going to be a pretty straightforward equation, pretty straightforward calculation. And again, when you're doing these tables, when you're filling out these, when you're filling out these tables, when you're doing these charts, and then you're putting them onto graph form, you're basically just doing a bunch of evaluation questions. And so what that means is it's just like with the first and second assessment. You're being asked to evaluate this function at x equals -2, and then you're going to write the answer here. Evaluate this function at x equals -1, and then write the answer here. And all we're doing is we're getting data points that we're eventually going to put onto a graph. So, again, because we're basically just being asked to evaluate exponential functions, we're going to do the exact same thing that we've done since day one. Dealing with this, we're just going to read it. We're going to go from left to right, and we're just going to put in the numbers as we see them. So 0.5, and I'm going to do the little up caret there, -2. Okay, that's going to give me 4. Okay, clear out. And I'm going to do 0.5 up arrow -1. That's going to give me 2. With this one, I'm not going to do the calculation. It's the same sequence of numbers, but what you should know just as a concept review is if you have an equation like this and you raise it to the 0 power, the only term that's in the equation is the one that has the exponent attached to it. And anything that you raise to the 0 power automatically equals 1. So I don't even need to use the calculator for that one. At the same time, I don't really need to use the calculator for this one either, because 0.5 raised to the first power is the same as the number itself. It's the same as 0.5. So, and now I know what 0.5 to the second power is, but we may as well get the practice in. So 0.5 up arrow 2 gives me 0.25. Alrighty. Now we've got to answer some questions about the initial value and the growth or decay rate. All of that information is available to us right now, so we may as well move forward with it. The initial value, normally when we have one of these equations, we have a times b and then to the x power. It looks like with this equation, we just have b. Like, again, the normal general equation is a is equal to a times b to the x. And by all accounts, we just have b. That's all we've got. We just have b. Well, we also have a. It's just that a is a value that doesn't make a difference. It doesn't make a difference whether we include it or not. And so that means that the initial value is going to be 1. I know the instinct of some folks is to say, well, if the initial value isn't there, it must be 0. Okay, well, let me ask you this. If the initial value is 0, what is 0 times anything? It's going to be 0. And so if I'm right and a equals 1, then f of x equals 1 times b to the x, which is the same as this. But if a is 0, then f of x equals 0 times b to the x, which is big ol' 0. So that's how we know that the initial value is 1 if we don't see anything. So if you just have b to the x, a is automatically going to be 1. Next, we have our growth and decay rate. We know that it's going to be decay because it's less than 1. So what I'm going to do is I'm going to do an equation that I started doing with one of the other worksheets that I carried over with assessment 2, and I'm going to go for, and I'm just going to do the form, I'm just going to show the formula. I go into greater detail on the growth and decay worksheets, I think with the other worksheet for the 2.2 assessment. But the equation is you take the absolute value of whatever is in the parentheses minus 1.0. Absolute value just means that whatever this is, positive or negative, the answer is going to be put out as positive. So if you use absolute value, it means that anything in here, even if it's negative, it turns positive again. So that means the absolute value is going to be 0.5. Whatever that answer is, I'm going to multiply it by 100% in order to get the percentage. So that means I've got a growth and decay rate of, a growth or decay rate of 50%. 0.5 times 100% equals 50%. So if I've got a 50% growth or decay rate, that means I've got to figure out whether it's growth or decay, right? The way that you figure it out is you take a look at the number inside the parentheses. If it's less than 1, you know that it's a decay rate. So I've got 50% decay. And there we go. That's the first section done. Now we've got to get some plotting in. As I mentioned before, it's like the x plane is usually just numbered by ones. And so this this is 0, and then 1, 2, 3, 4, 5, etc. The y's can change their scales however they want to. I'm going to use the same scale where each box represents 1. So this is f of x equals 1, 2, 3, 4, 5, 6, etc. So let's get started. I've got -2 and then 1, 2, 3, 4. Because this line here is where y equals -4, and this is where, not -4. This is the line that equals 4, and this is the line that equals -2, so I'm just going to put a dot where the two lines intersect. -1, and then 1, 2. 0 and 1. 1, so 1 on the x here, and 0.5. And then 2, 0.25. With the decimals, you kind of have to eyeball it. But again, we're not looking for absolute precision. We're just looking for illustration of a general trend, which for that sort of thing would be perfectly fine. Now we go over here, and we're answering questions about the graph as it exists. Well, first of all, growth or decay, kind of asking the same question twice, but it's almost like the person that put together the worksheet wasn't paying attention. So you have growth or decay. So it's a decay. And it's decay because the longer you go, the smaller the number gets. Then we go to the domain. The domain again is all possible x values. So if you wrote -2 to +2, you're not technically wrong because those are the only values that we put in. But when we're talking about domains and ranges of exponential functions, we're looking at specifically what possible values could you put in order to get a number out. And so is there a limit as to what numbers we can put into this equation that will affect the numbers coming out of the equation? So are there any limitations on what x value we can feed into this equation? Is there anything that says that we can put in x equals -50, x equals -100, but we cannot put in x equals -500, for example? Or is there a limit that says we can't put in x equals 5,000 into this kind of an equation? There isn't, and there isn't going to be. Generally, especially for this assessment and for the stuff you're going to be doing, the domain is always going to be -infinity, infinity, positive infinity, or if you just wanted to, if you didn't want to mess with negatives and positives, you can just write infinity and that'll be perfectly fine. It represents the same thing. So what that means is you can put in any x value you want. You can make it as negative as you want. You can make it as positive as you want. It doesn't matter. You can always feed in an x value onto this formula. So the range. Now the range is a little bit more complicated. The range deals with up-down values. The range deals with y values. So what that means is there a maximum y value that we can achieve? Is there a number? Is there an x that we can put in where all of a sudden we get to a vertical point? We get to a point on this vertical line where we put in an x, and then we just can't go any higher. We can't go any higher than where we are right now. The answer is no. If we can put in whatever x we want, then that means that it's going to output a larger and larger y value. So there is no ceiling. There is no upper limit as to what y can become. Now be sure that you're not confusing negative y with positive y, because as x goes negative, at this point, y is still positive. Y is positive from this point here all the way up. And so even if x goes negative, y is going to keep going up and up and up and up. Y goes negative when it comes below this line. So if you have point 1, so if you have point 1, negative 2, so if you're looking at a graph of 1, negative 2, x is going to equal 1, and then negative 2 is going to be right here. It's going to be down here. It's going to be this point. So y is negative when it's below this line. But if it's above this line, whatever the value is, it's going to be positive. And so what that means is that its range has a floor. The range has what's called a floor. It has a point where it goes lower, and then it cannot go any lower from there. And that value is going to be 0. This will never get below 0. This will never achieve 0. So 0 is going to be the bottom of the, it's going to be the floor. It's going to be the bottom of this equation. But like I said, if we can put in however large an x we want, we're going to get out as large a y as we want. And there is no upper limit for the y. So that means our range is going to be infinity. Our y-intercept. When we're looking at y-intercepts, we are looking at where our line here crosses that big black vertical line here. And so if you have x equals 0, whatever that value is, that's going to be your y-intercept. Let's see. Now we have to worry about the asymptote. On the assessment preparation that we did the day before the assessment, I did a deep dive into what the asymptotes were, what to look for, how to find them, and what the values are. The PowerPoints are on Canvas, and I suggest that you take a look at those if you want to get a better understanding of them. Like I said, I go into a deep dive with them. But in this case, I'll do a quick summary of it. If you have an exponential graph, you have a graph with two tails. You have one, and just starting here at y equals 0, starting here at x equals 0, excuse me. You have one tail that goes up and up and up and up until it's practically vertical. You have one end that goes down, 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 down until it's practically horizontal. The asymptote is the horizontal line, and it's the value that it tries to achieve but never can. And so we're looking for so if we're looking for the asymptote, we want the one that's horizontal, and we want the number that it tries to get to but never will. And so the asymptote in this case is going to be 0. And that's all that you would write down for it. So identifying the asymptote is step 1, and then but the value that you would write down on the assessment and that you would write down on these worksheets is the value that it tries to get to, but it actually can't. So that was a pretty deep dive into this first graph. So let's take a look at some of these other graphs, and we've got plenty to get through. So with this one, all right, got something a little bit different here. With this one is a lot more like our general equation, f of x equals a times b to the x. So what that means is if we have a, that means that we know what our initial value is. Our initial value is going to be 2. All right. And I can actually do the growth decay rate while I'm here because I can just plug it into our equation that I talked about in the space above. So that means 1.54 minus 1.00, take the absolute value of it, means I've got 0.54 times 100%, gives me 54%. And is the number greater or less than 1? It is greater than 1, so that means I've got growth. And growth. I just went ahead and circled that while I was here. All right. Now we're going to get to filling in the table, getting some points on our graph. Make sure I get this centered. All right. So again, all I'm going to do is I'm going to make the calculator do all the work. I'm going to make it do all the heavy lifting. And the way that I'm going to do it is I'm going to read this f of x left to right, just as it appears, and I'm going to punch in the numbers as they show up. So 2 times 1.54, up arrow, instead of x, I'm going to put in -2. And it gives me 0.84. I'll just say 0.84. Okay. Now I'm going to go for 2 times, make sure it's centered. Yeah, we're good. 2 times 1.54, up arrow, -1. Okay. I'm going to say 1.30. When this is 0, that means that this term becomes 1, so I'm just going to get 2. So for 1, so for x equals 1, that means I'm going to get 2 times 1.54, and I don't have to mess with an exponent, because anything raised to the first power is just equal to itself. So this just means 2 times 1.54, 3.08. And then finally, 2 times 1.54, up arrow 2. I'm going to say 4.74. All right. So now that I've got those points, I'm going to graph them. The same way that I did up above, I'm going to say that each unit, each box going left and right is going to equal 1. Each box going up and down is going to equal 1. And so that may make some things tighter that may make some things tighter as far as other parts of the graph are concerned, but I think we can work around that. I think we can work around it. So, if x equals -2, then y is going to equal 0.84. I figure that's going to be right about here. If x equals -1, then y equals 1.30. We'll put that just above the quarter mark. If x equals 0, y equals 2. Let me round that out a little bit. Y equals 2. If x equals 1, that moves us up to 3.08. So 1, 2, 3, just a little north of 3. And then the last one, if x equals 2, then we have 4.74. 1, 2, almost caught it there. 1, 2, and then 1, 2, 3, 4.74. Put that right there. And there we go. That is our growth formula. So we're going to go over and we're going to start answering questions about this growth formula. What is its domain? Again, the domain is what are all the values that you can put into this function that will produce an output. So the domain is just going to be infinity. Most of the domains you're going to run into are going to be infinity, but I wanted to discuss what the decision-making process was in terms of defining what the domain is. I can't speak to every single problem you're ever going to run into, but if you know that you can put in any x on regardless of how negative it is, or any x regardless of how positive it is, then that means that your domain is infinity. Now the range, much like the problem above here, the range is going to be what are the possible y values that you can have. Now this is an asymptote, and it gets smaller and smaller and smaller going in this direction. And so what that means is that what value is it trying to reach that it just can't reach in general? Well, if you're looking at an equation that has a times b to the x as its primary shape, then your asymptote is going to be 0. I'm just going to write that down here while I'm at it. But that means that if the asymptote is 0, that also means that the lowest possible value you can get is 0. Because if your range defines all the values that are possible with this function, if your asymptote is the lowest possible value that you can achieve without actually getting to it, then your asymptote and your range should have the same lower boundary. These two should be the same number as they are right now. Now, is there an upper range for y? Is there a limit to what y can be depending on what x is? Well, x can be infinite, so x can keep going this way as long as it wants to, which means y can keep going up to match it as long as it wants to. So the upper boundary of a y is going to be infinity, because there is no limit. There is no limit to what y can be as it shoots off into, I'm not going to say oblivion, but as it shoots off into the heavens of plane coordinate reality. There's no upper limit for it. Now, y-intercept. The y-intercept is, again, where our plotted line intersects with the big black up and down line, or the y-axis. And so it's going to be 2. Now, here's something that, now I'm going to discuss something that some of the more eagle-eyed folks may have spotted already. Excuse me, I had to do a bit of a stretch there. If our initial value is 2, and our y-intercept is 2, is our initial value always going to be equal to our y-intercept? Not always. The initial value is always going to stay the initial value no matter what. So when you have an equation like this, where you have 2 times 1.54, the initial value is always going to be 2. There's nothing that's ever going to change it. It is always going to be your initial value. That's just the end of it. It's never going to be 1. It's never going to be 0. The initial value is never, ever, ever going to change as part of the function. The y-intercept, however, can change. And the y-intercept will change if you have something like if you have an equation like this, and then you have plus 3. Then what that means is that the lowest possible value is no longer 0. That means that the lowest possible value is now 3. Not only is the lowest possible value 3, but this entire thing has shifted up, this entire line has shifted up 3 spaces, 1, 2, 3. So in this case, the y-intercept would now be 5. Because we take a look at this equation here, 2 times 1.54 plus 3. We set x equal to 0, it's 2 times 1, which is 2, plus 3. So at 0, the y-intercept would be 5. But this would always be 2. And so, like I said, your initial value is always going to be the same. Your initial value is never going to change. When you see it here, you write it down here, that's never going to affect it. But the y-intercept may be your initial value, but it's not always. And the only time that it would be different is if you have any function that has like a plus number or a minus number after this. If you just have this, or you just have f of x equals a times b to the x. If you have an equation of these forms here, like this form here, or the one, even the one above here, which is f of x equals 0.5 to the x power. Even if you have that, your y-intercept is going to equal your initial value. But it's really more of a coincidence, because this can always change based on your equation. This never will. This starts as your initial value, and it will start as your initial value no matter what. But it can change depending on what the formula is here. So that's an important thing to keep in mind. Is your y-intercept always going to be your initial value? No. But knowing the conditions under which it won't be is just as important as understanding that principle. Okay. Got a few more graphs to get through, so I'm not going to blaze through them per se, but if you want a more detailed explanation as to the decisions I'm making and what I'm doing, you can always slow down, rewind the video, or watch the first 2 problems in more detail, because a lot of what I'm going to go over in relatively faster speed is going to be the same, is basically going to be the same process. All right, so we'll start out. I'm just going to read it from left to right. Oh, first things first, I've got some information I got to record down. So I've got 0.02, so that's my initial value. I've got in the brackets, I've got in the parentheses 3.5, so 3.5 minus 1.0 equals 2.5 times 100% equals 250%, and it's going to be growth. All right, boy, we're just going through that. I mean, just with everything that we had here on the equation, we managed to fill in a pretty good chunk of the worksheet. We can actually fill in a lot more, but we can fill in a lot more, but one thing at a time. So let's get started. We're going to start by evaluating these expressions. We're going to start by evaluating this function. Again, I'm just reading it left to right, plugging it into the calculator exactly as I see it. -2 minus 3. And that gives me negative, I'm just going to say -3. Just make it easier for the rounding. It's important to note that this is 2.998, and it's not -3. And I'll say that that's important for a detail we'll get to later. So -1, so I've got 0.02 times 3.5, up arrow, -1, minus 3. Let's see, 2.994, all right. Let's see, 0. So that means that this turns into 1. So I've got 0.02 minus 3. So that's so that's negative 2.98. All right, I'm hoping to see a little bit more change. So 0.02 times 3.5 minus 3 equals, okay, 2.93. Oh, thank you so much. That's really making my day now. Let's go with 0.02 times 3.5, up arrow, 2 minus 3, negative 2.7. All right. Negative 2.76. Why not? So this is what I was talking about when I said that the y-axis can be whatever you want to. And in order to demonstrate what I'm talking about with the graph, I want to be able to show a general trend. But if I set the y-axis to each space equals one whole point, then all the points are going to be mashed together. You're not going to be able to see anything. So what I'm going to do is I'm going to set this equal to 0. Well, actually, I'm not going to set it equal to 0. What I'm going to do is I'm going to set it equal to negative 2.5, negative 2.6, negative 2.7, negative 2.8, negative 2.9. So does this mean that there are some values that aren't going to make it on? Oh, actually, yeah. No, you know what? No, I'll tell you what I'm going to do. I'll tell you exactly what I'm going to do. I'm going to set this to negative 3, then negative 2.9, negative 2.8, negative 2.7, negative 2.6, and that's as high up as it needs to go. So yeah, that's what I'm going to do. And you can do that. You can get away with that. This is the x-axis. But the thing is, the x-axis defines when y goes from negative to positive. You can set the y values to anything you can set the y values to anything you want. The x-axis is just an arbitrary point. Like I said, I misspoke. The x-axis is just an arbitrary point that says where y goes into positive or negative. You can ignore the x-axis completely and just set your scales to whatever you want them to be. The key is that whatever you set your scales to, you have to be consistent. And so, so that's exactly what I did. Each space, I'm starting at negative 3 here, and then each space represents 0.1 as I go up, because each one is negative, so this is negative 3, negative 2.9, negative 2.8, etc. This is perfectly legal in the world of math. So now I can plot some of these points. So I've got negative 2, 3. I've got 2.99. All right, well, maybe 2.98. then 2.93. I probably could have picked a better metric here. Then, let's see, 2.93 and then 2.76. Oh, all right, here we go. So 2.76. There we are. That's what I was looking for. There we are. I know that it's 250% growth, so I know that that's the direction that everything's going to go into. The one thing that I did mess up, though, is I need to be a little bit more. There we go. The reason I did that is because -3 is the because -3 is going to be the asymptote. That's going to be the value that it's the lowest possible value that it tries to achieve, but will never actually do that. So went ahead and wrote that down as -3. Now, how do I know that -3 is the asymptote? Like I mentioned with one of the earlier problems, if you have the general form, f of x equals a times b to the x, if you have this general form, then your asymptote is going to be 0, because the numbers that you get aren't ever going to go into the negative, aren't going to go into the negative realm. The only time your asymptote is going to change is if you have a times b to the x, and then you have something else here. If you have something else here, that's going to change what the asymptote is, that's going to change what the y-intercept is, and so it's going to shift everything up or down depending on what the value is. And so if it shifts everything up or down, it's going to shift the y-intercept. It's going to shift the asymptote. It's going to shift where the graph has its spike, as opposed to it's not going to affect what the graph looks like. But what it's going to do is it's going to affect where the graph is. And so that, in turn, will affect the y-intercept and the asymptote. So the y-intercept in this case is going to be -2.98. The range, as I mentioned with the previous problem, is going to be the asymptote value at infinity. And the domain, what are the possible x values I can feed in? That's always going to be infinity for the problems you're going to be dealing with. All right, got this next one centered. All right, I'm going to go through. I'm going to fill in the information that I know I've got. That means I've got, for the initial value, I've got 4.5. I've got 0.75, so I know it's going to be decay. I'm going to do 0.75 minus 1.00, 0.25 times 100%. That equals 25%. And I know it's going to be decay. And I know it's decay because I circled it over here, but also because this is less than 1. All right, so we've done pretty well for ourselves. Well, there are a couple other things I can fill in here. The asymptote, again, is going to be 0. And the reason I know that is because this is just a times b to the x. I'm not dealing with -3 or +2 or anything else. This is just the general form a times b to the x, and so the asymptote value is going to be 0. So let's see I can fill in a few other things too, now that I think about it. The domain always going to be infinity because there aren't going to be any limits to the possible x values that you're going to run into. The range, as I mentioned before, is going to be the asymptote for the lower end, and then infinity for the other end. All right, so all we have to do is figure out the y-intercept. Oh yeah, and our table of values, and we'll have to plot the graph too. Yeah, it's always the small things that catch you. You always forget the minor details. So again, I'm going to let the calculator do all the heavy lifting. 4.5 times 0.75, up arrow, -2. Oh, that gives me 8. Alrighty, off to a pretty good start. So 4.5 times 0.75, up arrow, -1. 6. Okay, I'm starting to see the numbers go down. This makes sense. As you go from left to right on the graph, as you go from negative to more positive, I'm seeing the numbers go down, which makes sense because this is a decay function. That's going to be, if this is 0, then that's going to be 1, and so the value is going to be 4.5. And because I just have a times b to the x as the form, for reasons that I mentioned in one of the earlier problems, this is going to be my y-intercept. So 4.5. Let's see, 4.5 times 0.75. Here's that one, and then 4.5 times 0.75 up arrow 2. That's going to be 2.53. All right. I think what I'm going to do with this one is I'm going to let each vertical space represent 1. And I'm going to let this y equal 0. I'm going to let this x equal 0. So now all I'm going to do is I'm going to plot it. So at -2, I've got 8. So 1, 2, 2, 3, 4, 5, 6, 7, 8. -1, I've got 6. 1, 2, 3, 4, 5, 6. At 0, I've got 4.5. 1, 2, 3, 4.5. At 1, I've got 3.3. 1, I've got 1, 2, 3. I'm going to say that's 0.3. And then at 2, I've got, and then at +2 for x, I've got 2.5 for y. So 1, 2.5. There we go. We've got a good decay graph. Again, even though the asymptote doesn't look like it's getting 0, I assure you, if we put in a large enough number, it's going to be very close to 0. So let's go 4.5 times 0.75 up arrow. My standard go-to is 50. And you see that it is a tiny, tiny, tiny decimal. It is as small as it can it is super, super, super small. If I did this to 100, I would definitely get 0 because of how the calculator rounds values off. But I'm not going to do that because I kind of illustrated my point here. Even though the graph doesn't look like 0 is going to be the asymptote because of how high up it is, I assure you, 0 is the asymptote, as demonstrated here. You use a large enough x. The way that the logic behind this is if you use a large enough x, you're going to get super, super close. The bigger the x, the closer you're going to be to the asymptote. And so when I did 0.75 to the 50th power, I knew that I'm going to be way down here. I'm going to be way down at the far end of the graph. And so because I know that, so the value is going to get closer and closer and closer to 0, but it's never going to actually make it. And so here it is really, really close to 0 because I don't even know what the decimal place is for this, but it's really close to 0 because it's just a minor, small amount above 0. So that's how I know that the asymptote is, in this case, going to be 0. And it's another way to check yourself if you're unsure. Okay. Next graph, again, I'm going to start going through these a little bit faster because we've already gone through a lot of these principles in depth. So it's just going to be applying the principles that we already know to a different set of information. So here I'm going to go. Let's see. I've got the initial value. I've got the growth decay rate. I can eyeball this. I know it's going to be 3% growth. The domain is going to be infinity. The asymptote is going to be -2, which means if the domain is infinity, the bottom part of the range is going to be -2, and then the top part is also going to be infinity. Whoops, it's like a duck wearing a mask. There we go. So that's all stuff that we can get just off of the equation. That's all the information we can get just off the equation. Initial value 1, all right. Growth decay rate, this is greater than 1, so I know it's going to be a growth, which is why I circled this. And you do enough of these, you can start to eyeball them. 1.03 minus 1 is going to give me 0.03 as evidenced by the other problems back there. 0.03 times 100% is 3%, so 3% growth. Like I said, there we go. Like I said, you do enough of these and you start to be able to eyeball them pretty quickly. Now I just got to figure out what the y-intercept is, and I got to figure out what the graph looks like. So again, I'm just going to put these things in as I read them. I am, however, going to ignore the 1 times because it's not going to have any bearing or any impact on what the final answer is going to be. So let's go with 1.06 negative. Oops. up arrow, -1, -2, 1.03. Oh, -2. Nope. It'd be -1. I'm talking to myself, but if this is 0, then that means that this cancels out into 1. And I have 1 times 1, which is also 1. And then 1 times 1, which is 1, minus 2 is -1. So I tried to do a bunch of mental math all at once, and I got it right. I got it right eventually. 0.3 minus 2, 0.97. Zero 3, up arrow 2, minus 2, 0.9, I'll say 0.94. Oh, this one's going to be pretty rough too. So what I'm going to do, I'm going to start with, I'm going to set this one equal to negative 0.9, 0.9, wait, no. That's right, that's what I'm going to do. I can set this one equal to negative 1.06, 1.05, 2, 3, 4, negative 1.0, 1, 2, 3, 4, 5, negative 0.95. There we go. Okay, yeah. That'll be a decent enough scale. Yeah, that'll work. So what I did was I defined this bottom range here as 1.06. And then I said this point here, directly above it, is negative 1.05. And so as I go up, I'm becoming more positive, which is how graphs are supposed to go. And so I did negative 1.06, negative 1.05, 4, 3, 2, 1, negative 1.0, 99, 98, 97, 96, negative 0.95. And so what I did was I zoomed in. I more or less defined my y scales by each box represents a tenth of a point. And then I just focused in on the relevant space of the graph that I wanted to focus on. And again, you can set your y coordinate, you can set your y scale to whatever you want to in order to help make the problem more clear. Oh, on here. But the goal is, but you need to be able to illustrate a general trend. So at negative 2, it equals 1.06. One of the best decisions I ever made. Negative 1 represents 5, 4, 3. At 0, it's negative 1. At 1, it's 9, 7, so 5, 6, 7. And then at 2, it's 9, 4. All right. So this one looks like it's going to be a straight line, and that's not too surprising. We don't have that big of a growth rate, and so what we basically have, we don't have that big of a growth rate. So for every single x we don't really have that big of a change. We don't have that great of a change. As a matter of fact, now that I'm looking at f of x, we don't have any real change per se because of how small the growth rate is. The change that we have as we go across is actually equal to 0.03 as we go. So this is, this is more or less a linear shape, but we're plotting but it's a growth. We're plotting the values as we see them. And the thing is, even with the sharpest curve, even with the strongest curve, if you zoom in close enough, which is exactly what I did here with the scales that I defined, if you zoom in close enough, you're going to get a straight line, even on any curve. So as long as you are consistent with what you're spacing them out to be, and you're clear with what the label is, you can label the y-axis whatever you want to make the graphing easier. But if all you did was if all you did for like the assessment or something else was you just drew a straight line and you didn't label any of the axes or do any of the points, I'd be like, well, it's not supposed to be a straight line, it's supposed to be a curved line, so minus all or something like that. I guess it depends on what kind of a mood I'm in. So we'll move on to the next problem. Hopefully we'll see a little bit more of a change with this one. It's always embarrassing when you try to do an exponential problem and you end up graphing a perfectly linear one. All right, so here we go. We've got the initial value. Initial value is going to be 2.5. That is never going to change. Growth or decay rate. Inside the parentheses, I've got 1.8. I know this by eyeballing it and doing enough of these that I know that it's going to be 80% growth. I've got minus 1.5, so that's going to affect the y-intercept, but it's also going to affect the asymptote, because now the asymptote is going to be equal to negative 1.5. That's going to be the smallest possible value that it will ever get to, that it will try to get to, but it never will, which means that the range is going to be negative 1.5 to infinity, and the domain is again going to be infinity. So now that we have all that information, let's start evaluating our table. So again, since we're evaluating things with exponential equations, we're just going to let the calculator do all of the heavy lifting. I'm going to write it in just as I read it, 2.5 times 1.8, up arrow, and then in this case it's going to be minus 2, oops, nope, minus 2, and then minus 1.5. So negative 2 minus 1.5 gives me negative 0.73. So again, just reading it from left to right. Okay. And we'll do a quick reality check here. The values as I go from left to right, so as I go from left to right on X, the values are negative, but then they're becoming more positive, so they're increasing. Since I'm working with a growth form, that makes sense. That checks out. That means that my math is going right. That means that I'm doing everything correctly. X equals 0. Again, we should be able to do this in our heads by now. X equals 0. That means that this term is going to be equal to 1, and so 2.5 times 1 is equal to 2.5, and then we subtract 1.5 gives me 1.0. And with x equals 0, that means that that is our asymptote, or not our asymptote, our y-intercept. And you don't have to put the 0.0 in there like I did. I just chose to because I've got so many other decimals everywhere else. All right, so 2.5 times 1.8, let's see, minus 1.5. That would give me 3. All right, I'm starting to see a pretty substantial jump here. So 2.5 times 1.8 up arrow 2 minus 1.5, 6.6. All right. All right. I am going to, the scale that I'm going to use, left and right, is still going to be one x value per space. So I'm going to keep that. For the y values, I'm going to keep that too. I'm going to do one number per space. So 1, 2, 3, 4, 5, 6, traditional numbering for a graph. So at negative 2, I've got negative 0.73, so I'm going to put that right about here. Negative 1, negative 1, negative 11, put that there. At 0, I put 1, so you can see we've already got a bit of a jump there. I've got 1, that gives me 3, 2, 3. If I've got 2, that gives me 6.6. So 1, 2, 3, 4, 5, 6. Okay. Draw. That's close enough. And again, I know that and we're going again for the general shape, and we know that the asymptote is equal to negative 1.5 because of this equation, because of this form, we know that the lowest possible value is going to be negative 1.5. It used to be 0, but now it's negative 1.5, so that's what we put in for the asymptote. And again, if you want a more detailed explanation, just rewind and one of the earlier problems. Two more, and we're done with the worksheet. That's really more for me to know. so I can case myself here. All right, so 3 times 1.2 to the x. What can we spot immediately? Well, I know that my initial value is 3. I know that I have a growth rate. I know that it is a 20% growth rate. Again, you do enough of these growth rate problems, you can solve through them pretty quickly, but just for personal edification, 1.2 minus 1.0, take the absolute value of it, that gives me 0.2 times 100%, and that gives me 20%. So, again, just using the formula on this page, domain is always going to be infinity. The range is going to be dependent on what the asymptote is, but the asymptote in this case is going to be 0 because I just have a times b to the x. I don't have plus c minus c or anything else like that at the end. The y-intercept is going to be 3, and I know that because the initial value is 3. Remember what I mentioned earlier. The initial value is 3, the y-intercept is 3 if you just have it in the form a times b of x, which is what we do. The range is going to be the lowest value from the asymptote all the way up to infinity. So, if we have this form of our function, of our exponential function, and we have to graph it, we've got all of this information before we've evaluated or plotted a single point. So that's pretty handy. That's pretty neat. So again, we're going to evaluate the functions, and we're just going to go one step at a time, one point at a time. So 3 times 1.2, up arrow, and then I'm going to start with negative 2. Okay, I'm going to say 2.08. Three times 1.2, up arrow, negative 1. Whoops. 3 times 1.2, up arrow, negative 1. There we go. 2.5, all right. And again, just to do a quick reality check, I have a growth rate, and then as I go from negative 2 to 1, the number is getting larger. So I know that I'm doing the right thing here. Let's see, 0, that should give me 3, because if x equals 0, then I can cross this out, it becomes 1. 3 times 1 is 3. For 1, that's just going to be 3 times 1.2. Gives me 3.6. And finally, 3 times 1.2, up arrow squared, 4.32. Alrighty. Yeah, we got a pretty decent jump here. So again, I'm going to let x, the horizontal axes, be 1, 2, 3, 4, etc. I'm going to do the same thing with the vertical axes again. I'm just going to see what this drawing looks like. So at negative 2, I've got 2.08, so really close to the bottom here. At negative 1, I've got 2.5. At 0, I've got 3. At 1, I've got 3.6. And then at 2, I've got 4.32. So 1, 2, 4. So you can see kind of a curve. That's good enough. You can see kind of a curve with that, and that makes sense because it's a growth, and we're good to go with that. So yeah, we got everything else that we needed to just off of the basic information that we had at the start. So let's keep it going. We've got one last one here to hit. So again, let's take a look at the information that we have with f of x, and we're just going to work through we're just going to get some information done here. So the initial value is going to be 4 because that's what the a is. The growth of decay or rate of growth or decay. There we go. Inside the parentheses, we have 0.85. So I know it's going to be decay because it's less than 1. But I also know that it's going to be a 15% decay rate because that gives me 0.85 minus 1.00. Take the absolute value of that equals 0.15 times 100%. And that gives me 15%. Like I said, you do enough of these, you start picking things up pretty quickly. Domain, as ever, is going to be infinite. The asymptote is going to be a little bit tricky because it used to be that if we subtracted it, then that meant that the lowest value was going to be lower than 0. But what if we add it? Well, that just means that the upper value is going to be lower than 0. That just means that the lower value is going to be greater than 0. As a matter of fact, it's going to be 0.5. That is going to be the lowest possible value that we can get with this equation in this function. So what that means is our range is going to be 0.5 all the way up to infinity. And I can't, and because I've got that extra thing here, I can't intuitively well, actually I probably can. But anyway, if you have this, then take your time filling out the table. Don't try to do too many shortcuts, because yeah, you don't want to make a preventable mistake. So, in the spirit of not making a preventable mistake, I'm going to let the calculator do the rest of the heavy lifting here. So I got 4 times 0.85, up arrow, -2, plus 0.5, and gives me 6.03, all right. Four times 0.85, up arrow, -1, plus 0.5. There we go. 5.21. And again, we're doing a quick reality check. We're working with a decay rate. So what that means is that as we go from negative to positive, as we go from -2 to +2, is the number getting bigger? No, it's not. It's getting smaller. So that's how we know we're working with that's how we know we're working with decay rate. So with 0, this term becomes 1, and so that gives me 4 times 1, which is 4, plus 0.5, which is 4.5. And that was what I meant when I was looking at that. And I said, I can probably do this in my head, but I wanted to go through and do the table properly. But with this simple of an equation, yeah, you can figure out what the y-intercept is, especially if you're taking out the rate anyway. So bring the calculator back. I've got 4 times 0.85 plus 0.5. Oop, oop, oop. 4 times 0.85 up. No, I was right before. Times 0.85. 0.85 raised to the x power. If x equals 1, it just equals 0.85. So I was right in the first place. I just didn't trust where I was going. Equals 3.9. And then finally, 4 times 0.85, up arrow 2, plus 0.5, and that should give me 3.39 already. So 3.39, and that will finish off our table. Again, we're going to do a quick reality check, make sure everything works out here. We're mapping a decay, and so if we're mapping a decay, then as we go from -2 to +2, that means that the numbers are going to get smaller and smaller and smaller, which, like I said, makes sense. We're seeing that. That's what we're doing. And so, like I said, everything's checking out. We're doing our reality checks and everything's working. So, since everything is working great, we can go and get started on the graphing. There's enough of the spread with the numbers that I think I can get away with doing. X is always going to be in integrals of 1. I think I can get away with doing integral up and down of also 1. So let's go ahead and get started. So -2, 1, 2, 3, 4, 5, 6. I'm just going to put this right on the dot here because 3/100ths, there's not going to be much of a difference between that. Let's see, -1 and 5.21. I'll put that just under the quarter space. 0 and 4.5. 1, 2, 3, 4.5. And then 3.9, and then 3.39. Well, let's see, 18, 20, okay. I was doing some of the math. All right, this is going to be a pretty, oh, wow. I think that's one of the nicer curves that I've drawn by hand. But, yeah, there it is. That's the final graph. That's the final curve on the final graph showing a decay rate. And I got to be honest, I'm probably, after I turn off the video, I'm just going to sit here and stare at that curve for a while. But yeah, there we go. That's the final decay curve that we've got here. And that's it for this particular Assessment 2.2 worksheet. Hopefully it's been some help to you. And yeah, I will see you next time then.